Yep. Right.
Very hard to see
elevator.
it.
Yeah.
Silver lining.
Okay, what's that? Okay, good.
We're here.
Okay, so it is my pleasure to introduce, sorry, Pete.
You're good. Yep, you're good to go.
It is my
Thanks.
pleasure to introduce Quinn Bowman. Quinn is in his third year, and this is kind of his AP process seminar. Not kind of, it is. Quinn did his Quinn's originally from Wisconsin, but he wanted to get away from Wisconsin for doing his undergraduate degree, and so he actually went to St. Andrews and did his bachelor's degree overseas at St. Andrews. And in the process, he got interested in, actually I think it was after your degree that you started doing the research, right?
Yeah.
Well, he got interested in atmospheric science and climate science and learning more about kind of the physical parts of climate-related science. And then after he graduated, he got involved in doing research related to, it was called the Dry Get Hotter. Yes, the Dry Get Hotter. And he had like a little kind of mini project related to that when he came here. And that has evolved into this work. We're no longer looking at dry heat. Now it's moist heat. But there is a strong climate change signal with moist heat, and he's going to tell you a little bit about the dynamics of tropical moist heat, some really interesting work that we've done. And this was also briefly mentioned in the colloquium, Monday's colloquium, some stuff related to this. So, yeah, you guys should all come to colloquium and hear these things. Okay, Quinn, take it away.
Sounds good. Do I need to turn on my mic?
You need to unmute it.
Okay.
Should.
Is that good?
Yep.
Okay. That's kind of loud.
Well,
Can you still hear it? Okay. Whatever. So yeah, as Larissa mentioned, I'm going to be talking about tropical moist heat extremes and like the dynamics of the tropical atmosphere and how that controls these moist heat extremes. So first of all, I'm going to start with what I'm going to be going over in this talk. First thing is I'm going to talk about what is moist heat, why do we care about it, and how do tropical dynamics constrain it. And then secondly, I'll be talking about how we're looking at it here, and some of this will be related to what Thea's talked about on Monday. Finally, I'll be looking at our results, and then what they mean, and that'll be that. So first things first, why do we care about moist heat? Humans care about moist heat because we partially cool down by latent cooling by evaporation. So the hotter the weather is, the more humans actually cool down by evaporation. And so for example, if the air temperature, dry bulb temperature, is hotter than human body temperature, you can only cool down by evaporation. And so that means that like a wet bulb temperature of around body temperature, humans can no longer self-regulate body temperature, and that you can't live then. So here on the right, I had a picture of a sling psychrometer. If you've taken Petty's thermodynamics, you might remember talking about this. And what you do is you put a wet cloth around a thermometer and you spin it around to get evaporation and latent cooling, and then when this wet bulb reaches equilibrium with the latent cooling, it reaches the wet bulb temperature. And so one interesting thing about moist heat is that it relates to partial thermodynamics. And so here in this figure on the right, which I've taken from, again, Petty's thermodynamics textbook, you can see how the wet bulb temperature is related to taking a parcel down in moist adiabat to the surface. And so we're going to be using that over this research to examine how this tropical stability constrains moist heat and human livable conditions. but I will mostly be talking about it in terms of moist static energy, which is related to wet bulb temperature in a very similar way. So what is moist static energy? Moist static energy is a measure of the static energy in an air parcel. And so here on this equation on the left, I have how it's actually defined, which is the latent heat, the specific heat, the latent heat, and the geopotential. And it's approximately conserved in convection as air rises and is unstable. It turns latent heat into specific heat and geopotential. And I have on the right sort of an idealized tropical moist static energy profile, which I will go through all the parts and explain shortly. But this is just sort of a vertical profile of some idealized tropical atmosphere. So first thing, this green line, we have the dry static energy. I'm going to use this pointer instead. Which increases as we rise, which is just the geopotential and the specific heat of a parcel, or of the atmosphere vertically. And then secondly, we have our moist static energy, which is the dry static energy plus the latent heat. You see that there's a pretty strong maximum at the surface, and then it decreases with height, and then it increases again in the upper troposphere. And finally, we have our saturation moist static energy, which is the moist static energy of the atmosphere, but if it were saturated. And so you can see that it's largely a function of temperature because it is dependent on the saturation mixing ratio of water vapor in the atmosphere. And so what we can see here, there's also some other lines here. You can see this black line is a idealized parcel path. So if we took a parcel from the surface, similar to if we were looking at like a SQT, and we lifted it up over this range is where this parcel has more latent heat than the saturated environment. And so this is shaded area here is kind of analogous to cake relative to a parcel lifted from the surface. And so this is largely the framework in which we're going to be looking at stability and moist heat for the rest of this talk. So, moving on now. One of the major aspects of tropical meteorology, which constrains moist heat, is called quasi-equilibrium. And so this is the idea that convecting atmospheres are approximately neutrally buoyant to convection on average. And this means is that when there's instability, that is surface moist static energy is higher than our neutrally buoyant parcel, then it is spontaneously removed. And so this generically says that the tropics cannot maintain instability on average. And secondly, we have weak temperature gradient. And so this is the idea that due to the weak Coriolis force in the tropics, the Rossby radius of deformation is very large, and that means that any instability radiates outward roughly horizontally homogeneously and smooths out temperature gradients. And so you have, as the name would suggest, a weak horizontal temperature gradient in the tropics. And so once again, if, as I mentioned earlier, the saturation moist static energy is largely a function of temperature, and so this means that the saturation moist static energy in the tropics is largely homogeneous, and I may use saturation moist static energy and free tropospheric temperature interchangeably over this talk. They're analogous. So what does this mean for our surface moist heat? Under strict quasi-equilibrium, which is our idea that in undilute convection, our atmosphere is approximately stable to undilute convection, we would see that as our surface moist static energy increases, so would our free troposphere equivalently. And so if we take our same idealized moist static energy profile, and we have this parcel at the surface, and we move it around as this moist static energy or moist heat increases, we would expect that it's constrained by our free tropospheric hemostatic energy, assuming it's neutrally buoyant. So this has been used to pretty good effect for the last few years in explaining some of our tropical heat. So here's a paper in 2021 which describes temperature under these dynamics, and you can see that it predicts that we'll have higher temperatures over land, or increases in temperatures over land and over the ocean. That some of that drier get hotter that Larissa mentioned in the beginning, that's some of related to the work I was working on before I came here. On the bottom left, we have a figure of how we expect this wet bulb temperature and surface temperatures to increase under global warming as we get free tropospheric warming and surface warming. It constrains this wet bulb temperature maximums by stability or land and ocean. And on the right, we have this was from a model which predicted wet bulb temperatures from atmospheric heating from El Nino. You can see there's quite a nice line where when you get strong El Nino events and atmospheric heating, you similarly get increasing observed surface wet bulb temperatures. However, this isn't quite an accurate way of looking at the tropical atmosphere, because while moist static energy is approximately conserved in convection, we don't get undiluted convection in the tropical atmosphere. This convection mixes with the atmosphere, which dilutes this moist static energy. And so what we commonly say is that we get entraining quasi-equilibrium, where the tropical atmosphere is neutrally buoyant to an entraining parcel. So this plot here is showing how, as you get updrafts and downdrafts, it mixes with the environment and decreases our latent heating of the parcel. So to show what this sort of looks like using that same plot, once again, this black line is our proposed undiluted parcel lifted from the surface. What happens is it mixes with our environment, this blue line here, and that decreases our moist static energy of our parcel. And we might get lines like these green lines as this parcel mixes with the environment until it detrains at the saturation moist static energy at various levels. And so this idea is that the atmosphere is neutrally buoyant to entraining convection, not an undiluted parcel. And so what this means is that if we take, again, the same plot, and we have some sort of instability where our surface parcel is more energetic than our 500 hectopascal instability, or temperature, that we don't actually get instability here because it's really dry in the lower free troposphere. That a parcel rising mixes and is diluted too much by the environment. And so if we think about this then in terms of moist heat, if the surface is not convecting, it's not removing that instability, it's stable because of how dry the environment is, we can actually get increasing instability up until it becomes neutrally buoyant and convex. And so, if we consider this surface moist static energy as being a measure of moist heat, this is how our moist heat is constrained at the surface by neutral buoyancy and convection in the tropics. And this is, again, a function of how dry the environment is. And this is important because we expect that relative humidity will stay roughly constant with global warming in the future. This has been shown by climate models and theory. But with increasing temperatures, we know that then saturation mixing ratios will increase, and the actual saturation deficit will therefore then also increase. And using this mechanism, we might expect that then we'll get increasing extremes at the surface due to entrainment and increasing saturation deficit. So that is our background and how these large-scale dynamics constrains surface moist heat. I'm going to talk about how exactly we use this background then to actually look at moist heat here. So first, I'll start with our neutral buoyancy under strict quasi-equilibrium. And I'm taking this methodology from this paper again that Fias mentioned, published in 2024, Duan. lead author. And what you can see here is that under our strict quasi-equilibrium, we would say that our moist static energy at the surface must be less than or equal to our free tropospheric temperature at neutral buoyancy. But we know that's not quite true. We also have adjustment by entrainment. And so if we have our surface moist static energy must be less than our free tropospheric temperature plus some modification, some adjustment based on this lower free tropospheric dryness. And so the way this W here is just how important our dryness is in our convection buoyancy.
And you probably want to say what Q minus is.
Oh, and Q minus, sorry if I didn't mention it, is saturation deficit. That is the difference between the environmental moist static energy, or the environmental vapor pressure, or not vapor pressure, moist static, or specific humidity and saturation specific humidity. How dry the environment is relative to saturation. So now if we take the same equation and then we decompose our saturation moist static energy here into the zonal mean, which is our weak temperature gradient component. So we assume that this is roughly constant across the tropics, plus some deviation from weak temperature gradient, which we assume is small. And so if we decompose this term then into this, we have our surface moist static energy must be less than or equal to our zonal mean free tropospheric temperature, plus some deviation from weak temperature gradient, plus some adjustment to buoyancy due to the dryness of the atmosphere. And then, so we take this and we rearrange it a bit. Oh, sorry, that might be hard to see. If we rearrange this, we put on the left-hand side our surface moist static energy minus our zonal mean free tropospheric temperature, which is again analogous to just an undilute parcels instability. And then this must be less than or equal to our saturation deficit adjustment plus our deviation from weak temperature gradient. So this is the equation we're going to mostly be using for the rest of this talk to quantitatively analyze the surface moist heat. And what it says basically is that instability cannot be greater than the saturation deficit plus some weak temperature gradient deviation, and our weak temperature gradient deviation is small. And again, this methodology is largely derived from Dawn's paper, which was quite recent. So we take this equation, and so once again, we want to look at surface moist heat. Let's take these two halves and let's plot them. So we want to understand how they relate to each other, so we're naturally going to put them on opposite axes. Let's put instability on the x-axis and our latent heating dilution, that is the saturation deficit component, on the y-axis. And we're going to look at our extreme days. So we're going to plot them here on this plot as a sort of scatter plot. And so again, in terms of words, we're saying that this instability term must be smaller than this latent heating dilution. So under strict quasi-equilibrium, we would expect that our entrainment would have no effect on our instability. And so on our most extreme convecting days, we would have close to zero instability, and it wouldn't be a function of our latent heating dilution or saturation deficit. However, so this is what we would expect if our latent heating dilution had no effect on our instability, but we know that it does. So we might expect something more like this, where our most extreme convecting days lie along the line here, whereas we get increasing dilution by latent heat, or by saturation deficit, we get increasing stability. So let's draw a line through this. And so this line, if you think about it, is sort of a ratio of how our latent heating dilution and our instability influence partial buoyancy. If we take this half the equation, we put it there. So W is sort of a ratio. And we know from empirical analysis or empirical results and relationships from reanalysis that the slope of this line is about equal to 1. That instability, or non-dilute instability, and latent heating dilution are approximately equally important to our partial buoyancy and instability. And so once again, this is our entraining quasi-equilibrium convecting buoyancy line, neutral buoyancy line. So now I'm going to show you a plot which, if you were here on Monday, you might have seen, but a bit modified. This is from the same paper, Duan 2024, and what you can see here is the same axes where we have this instability term on the bottom and this latent heating dilution term on the y-axis. And what you can see is that we have kind of what you expect. You get a increasing maximum of our days along this entraining quasi-equilibrium line.
What do the colors signify?
Where red is our scatter plot of our maximum wet bulb temperatures, and we have our distribution of all of our days in reanalysis.
In brown?
In brown and green, where green is precipitating days. And so we expect precipitating days are convecting, and so they lie on this neutral buoyancy line. But again, this is modified. I'll show you the full plot here. This is from actually their paper fully. And so this is pretty nice. We can see that reanalysis follows our theory pretty well. We have a maximum following our entraining quasi-equilibrium neutral buoyancy line. And then we have a whole bunch of days which don't follow it, which aren't convecting. They're stable for some reason or another. However, this relationship plotted here is only shown on a pretty selective set of data. It's shown on our climatological extremes over warm seasons, over a pretty small overall locations, which means that it's only in the most extreme moistatic energy locations, which are largely over like the tropical Indian Ocean near the coast, and so on. What I'm interested in, and what we'll be talking about, is how this relationship might explain more human-relevant extremes, things outside of just the climatological maximums in the most extreme areas. And so this is how we're going to be looking at this for the rest of the talk. And what I define as, I guess, how we're looking at it in more human-relevant extremes is, number one, do most of the tropics spatially respond similarly to saturation deficit, or is it just these most extreme convecting regions, which are shown in that previous plot? Secondly, do observations show the same relationship, or is it really just our grid scale and reanalysis relationship that we see it in? And finally, do extremes on a subseasonal scale, which I'm looking at monthly maxima here, respond similarly to saturation deficit, or only just the absolute climatological maximum? So the way we're looking at that is we're using weather stations with just surface weather stations across the tropics between 20 degrees north and south. I have all these locations highlighted here. We're going to be using the same scatter plot and entraining quasi-equilibrium equations that I showed earlier. But additionally, we're going to be doing a binning analysis to try to look at sort of the bulk relationships and how they vary outside of just the most extremes. One thing to note is that because we're using just surface weather stations, in order to use that equation we used before, it's going to be paired with ERA5, lower troposphere saturation deficit, and free troposphere temperature fields that are regridded to 1 degree and then interpolated in weather station locations, and it'll once again be compared to ERA5 surface reanalysis moistatic energy, similar to the previous work that I showed. So let's look at the results. First things first, this is a plot of our monthly maximum days in a similar way as our previous, the previous plot from Duan that I showed you just a few slides ago. And so on the x-axis here, we have our instability, which is, again, the left side of our equation here. And along the y-axis, we have our weak temperature gradient, our saturation deficit dilution, and our deviation from weak temperature gradient. And so we have a line of approximately equal to neutral, or strict quasi-equilibrium, where saturation deficit would have no impact on instability. And then we have our W, which is our slope, our ratio of how they impact buoyancy, equals one line here, which should explain our maximums of our surface extreme moist static energy, where we get neutral buoyancy. And so if we look at this heat map here, you can see that this works pretty well. So this is reanalysis on our weather station locations and times. So all of our monthly maximums from weather stations I interpolated onto reanalysis fields. And you can see that reanalysis across the tropics and our monthly maximums is described pretty well by our W equals 1 maximum line. And the star here is our average of all of our points. You can see it's pretty close to our maximums here because there's not a lot of data points outside. Mostly these are convecting days that are clustered very close to this maximum line. So let's zoom in on just the spot on the right because I think it's more interesting. You can see more in it. Well, I already did mostly talk about it, but yeah, you can see that this W approximately equals 1 line describes our maximums pretty well. And we can say that generally across the tropics, in reanalysis at least, we see mostly the same pattern. So now, how does this look in weather stations? Again, this is the same plot and same equations. You can see we have instability on our X, and we have our saturation deficit dilution on our Y. And what we see is quite a different relationship. So first of all, I'd like to note that we get way higher extremes here in our instability, which is mostly describing our surface extreme moist static energy. So again, look at how high these values are, and close to 50 kilojoules per kilogram in instability. And I'll go back to here, where we get 25 generally at a maximum here in reanalysis. The second thing I want to point out is that our maximums are way higher than our predicted maximum line this time. So here we have a black line of W approximately equals 1, or W equals 1 there. And then I have drawn a second line on here where W equals 2, which describes a different maximum which seems to qualitatively describe our maximum, where our impact of saturation deficit would be twice as strong as suggested by reanalysis. So again, let's zoom in on that heat map on the side because that shows our relationship better. This is really notable and it's really interesting because it shows that our weather station surface extremes are quite a bit higher than expected. So to bring this back to our human relevance, this means that our surface moist heat, which defines human livability, is much higher than what we would expect to see if we were just using model data. And so this is pretty interesting because, well, why? Why is this more unstable than we expect and should be defined by our equation? But I will get back to that later. And first I'm going to show you a binning analysis. So we did a binning analysis because of some of our research goals, which said we want to look at how all of the tropics vary in all conditions, not just our most extreme limit. And so by doing this, we're binning by zonal mean temperature at the weather station locations and the saturation deficit in the lower free troposphere at our weather station locations. We're binning by these terms in our equation. 20 bins in saturation deficit, that is 5 percentile bins, and 20% percentile bins, that is 5 different bins in zonal mean free troposphere temperature. Because we want to look at how this surface moist static energy varies across conditions. And again, we're assuming, or we know that this term is small. So here I have what these binning analyses show. And so this is a lot. I'll take my time and explain it. So again, we're binning by free troposphere temperature and saturation deficit. Along the x-axis in this plot, we have our saturation deficit bins. There's 20 bins along here that are not all the same size. You may note that this line is much longer than like this one. That's because there's just not as many dry days in the tropics here and our driest 5%. And so we are also binning by our free tropospheric temperature, zone mean free tropospheric temperature, and so we have 5 different bins. And so we have our coldest zone mean temperature is here, and then increasingly warm. And so what you see is that our coldest, or our driest, sorry, our moistest bins increase in in surface extreme moist static energy, that's our y-axis, with saturation deficit as expected. As we get drier moving along x, we get warmer in surface moist static energy. And where we get our warmer free tropospheric temperatures, we get warmer surface moist static energies. So this is behaving as expected. As this increases, this similarly increases, and as this increases, this similarly increases. However, you may note kind of an interesting relationship where as we get increasingly dry past about 15 kilojoules per kilogram in saturation deficit, it actually decreases on average in our bin average moist static energies at the surface. And so what we're expecting, what we are hypothesizing is that this is due to it being too dry and convectively suppressed. If you remember, quasi-equilibrium only applies to convecting atmospheres, and if these very dry days are not in a convecting atmosphere, we don't expect this to necessarily constrain our surface moist static energy, and it might be dominated instead by like radiative cooling over clear skies because it is so dry there might not be clouds. And one last thing to note here is that once again our weather stations, here the plot on the right, are systematically higher surface moist heat than our reanalysis across all bins. Okay, and so here I just talk about this again. You can see that this is our actual bin sizes. You can see that we have more moist bins than dry bins. And so one thing to note is that this plot should mostly be interpreted qualitatively because, once again, as I mentioned earlier, this equation does not constrain our non-convecting days, and we expect that using monthly maximums at all weather stations, there's going to be a lot of non-convecting days that we're taking in here. And so we can't quantify, using our methodology, how many of these days are convecting and how many are not. So we're mostly just looking at just the average variance. Finally, if we instead plot the instability, that is this whole term on the left here, we expect that this to be constant for a given saturation deficit, which is mostly what we see here. If we bin by instability, our lines of surface moist static energy, or our lines of instability mostly collapse on each other per saturation deficit, which is good. That's what we expect to see. One thing to note is you may see this bottom, this coldest free tropospheric temperature bin is quite a bit lower. And so this is again highlighting how this plot should mostly be interpreted qualitatively. We know that there's pretty significant sampling biases which are involved by binning like this. So for example, by binning our coldest zonal mean free troposphere temperature bin heavily samples our weather stations, which are higher latitudes, close to 20 degrees north and south, relative to our warmest bins, which are closer to the exact equator. And so our bins, which are weather stations, which are farther from the equator, are a bit more stable. And that's why we have lower instability. And this is actually pretty interesting then, because this shows that our spatial, our local climate to our weather stations can pretty heavily influence the actual statistics of moist heat and how often we get them, and so on. Because while these weather stations are being sampled preferentially to our higher latitudes, we can see we still see the same relationship, but lower moist heats. And this might be indicative that we just don't get these most extreme days as often outside of the deepest tropics. So those are the main results. Let's talk about what they mean. So again, to look at our science questions about our moist heat extremes. Question number one is, do most of the tropics spatially respond similarly to saturation deficit, or just the most extreme convecting regions? So I'm going to address these one by one, actually. Let's address question one, which I just stated. And you can see that on average, they do. We get increasing, for all of our bins, we get increasing surface extreme moist static energy with saturation deficit over our, what we're calling a convecting regime in the relatively moist area. But again, our local climate and how often we convect and can be really important to actually where we get these moist heat extremes. You can see that if we're in a really, really dry area, we might just not get these same moist heat extremes. It's pretty heavily modulated by the local climate. Question two is, do our point scale or observational results respond similarly to saturation deficit or just our grid scale and reanalysis? And qualitatively they do, because we do get a linear maximum in our results here. But it's at quite a bit higher line than we would expect. And so what this shows again is that we get a systematically higher moist heat at our surface weather stations than reanalysis would suggest. And we have some hypotheses about this later. Sorry. And finally, do our extremes on the subseasonal monthly scale respond to saturation deficit 2, or only our absolute climatological maxima? And again, we can see that they do in our moist convecting regime. But the local climate and how it interacts with convection in the area nearest to our weather stations can have important impacts on what we actually see from moist heat. And I just realized I did not mention what this black line is. One thing that if you remember earlier, is I talked about how we expect relative humidity to stay roughly constant with climate change. What this black line shows is our climate change signal, tropical mean saturation deficit, and moist heat over time. We can see that our tropical mean signal of increasing moist heat and saturation deficit over time is quite distinct from what our weather stations are showing, and quite a bit lower. So, where do our assumptions and this framework fail, and why are our extremes not that well described by our reanalysis? So, again, what we see is that we have a mostly well-described maximum, except we get higher instability in weather stations per saturation deficit than you would expect. And so we have four main hypotheses. Again, looking at our equation here, hypothesis 1 and 2 are related, and that's that reanalysis doesn't describe the actual conditions to our weather stations very well. There might be a problem of the actual representation is wrong, or that we have some sort of grid averaging, which is obscuring our actual maximums. And then we have hypotheses 3 and 4, or 3, which is that quasi-equilibrium, which is our main assumption we're making, describes these maximums. It breaks down on our point scales in our weather stations. And hypothesis 4 is that the reanalysis buoyancy sensitivity to saturation deficit for moisture is just too low. And that's why the W equals 1 line doesn't work that well. So first things, I'm going to show you the hypotheses 1 and 2, because we don't think that they are the reason why we see this signal, and they're related. So hypothesis 1 is that this part of our equation here is not, in reanalysis, is not accurate with the rest of this equation in using weather stations data. It's not consistent. So we know that lower free troposphere saturation deficit in the tropics, or moisture, has quite small spatial scales. And maybe one of the problems is that when we average out 1 degree grids, we don't see that small scale, and this and using the 1 degree saturation deficit is obscuring the actual maximums of saturation deficit local to our weather stations, and it's just not working out right because of that. And that's basically a problem that reanalysis just can't, might not be showing just a small enough scale of moisture structure. However, if we do the same methodology before, but we use 1 degree, or we use 1/4 of a degree, that's the native reanalysis, or not native, the smallest reanalysis scale saturation deficit, we see almost no difference in our results. And so what we would expect is that as we move down to 1/16 of, if this were the problem, if we move down to 1/16 or 16 times the resolution, and we would expect to see that we would get a result using reanalysis that approached our weather stations, or other way around. And because it's mostly the same, we think that that small-scale moisture structure is likely not the problem here. And a similar related problem is that maybe our reanalysis surface moist static energy is just poorly represented. It's just too low because of some grid averaging or so on. We know, however, that reanalysis assimilates this weather station data, so there's likely nothing physically wrong with our surface moist static energy averages. It is constrained by our observations. But we do have a problem where we are working on a grid average, and so our actual maximums will be obscured by using a grid average. But then this sort of leads to the question of what mechanisms lead us to actually get a maximum that exceeds what should be possible by this equation. Like, is this equation useful if it only works on the grid scale averages? So these are hypotheses 1 and 2, which we think are not really representative of the problems with, or the interesting aspects of this research. So now hypothesis 3 is that quasi-equilibrium, that is this inequality here in our equation, might not be a valid assumption to make when we're looking at point scales. Convective quasi-equilibrium is a statistical equilibrium over, again, our convecting atmosphere, our ensemble of convecting elements. So that would say that that's what constrains this instability. But we know that that's not quite how this works. We know that the positive instability is necessary for a single convective event, and it's not strictly constrained on small time and space scales by our quasi-equilibrium. And so here I have an actual moist static energy profile I took from just a random weather station in the tropics, and I plotted our moist static energy profiles. What you can see is that this 850 hectopascal saturation deficit, which you would expect to be, while convecting, equal to our instability, is quite a bit smaller. And so this shouldn't be possible following this equation, and yet we can see it in observations that it is. But that's because this equation doesn't strictly constrain single points, single convective events. And so this is one of the problems we're suggesting, is why we get larger maximums. And finally, is reanalysis moisture sensitivity just too low? That would be the W, the ratio of saturation deficit buoyancy impact, or saturation deficit impact on buoyancy to instability. And so with this plot here, or we can talk about this plot a little bit more. One of our hypotheses is that this 1 is not quite an accurate assumption when this is an empirical relationship for reanalysis, and it might not be accurate to what we see in observations. And so this plot on the right here, it's from Wolding, 2022, and I've modified it a little bit to be in terms of this equation here. And so what this plot is showing is we have this saturation deficit impact on buoyancy versus our undiluted parcel impact on buoyancy. And these purple lines here are 1-to-1. So that is that this half of the equation is equally important to buoyancy as this half of the equation. And that's what we would expect to see if the contours are related to actual buoyancy that we see in the atmosphere. And so what we would expect is that our contours would match up with this 1-to-1 line. Our observed buoyancy matches up to this theory of 1. And what we can see is that the contours don't. They're quite a bit steeper in terms of saturation deficit. These results from Moulding suggest that saturation deficit has a stronger impact on our parcel buoyancy than reanalysis suggests. And so there's some ideas with this. This W might actually be scale dependent. We had just talked with Fiaz on Monday, and that's one of the ideas he suggested, that as we move from a point scale to a grid scale, that might be another aspect in which quasi-equilibrium doesn't fully describe our buoyancy here. But this is one hypothesis. So we can't be sure using just our surface data what the actual problem is, but our main hypothesis is that it's some breakdown of quasi-equilibrium on small scales, or that the moisture sensitivity from reanalysis is just too low. So finally, let's talk about what this all means. The big problem here is that our point scale extremes are higher moist heat than we would expect. And so it's likely a problem that's a combination of these three issues that we can't fully solve, and that is maybe our grid convection parameterization is off, maybe the grid averaging of the extremes isn't describing the actual extremes well, and maybe our quasi-equilibrium is not actually holding to describe what the surface extreme moist heats are. But the big picture that I want to take away from this is that our entraining quasi-equilibrium neutral buoyancy equation, which we've used and showed, when it's conditioned on reanalysis statistics, it doesn't strictly constrain our surface moist heat. And so final conclusions is, this is a useful framework for understanding the large-scale tropics-wide moist heat extremes, but the actual small-scale extremes, which are human relevant, on the matter of survivability and days and single points, is not well constrained. And there might be several reasons, from poor buoyancy sensitivity and reanalysis, to grid averaging, to just quasi-equilibrium not necessarily holding. Secondly, the actual statistics of where and when we get extreme moist heat are highly dependent on local climate. And the most extreme moist heat does require some specific conditions, that it's moist enough to have moist heat and convect, but it has to be dry enough to suppress convection to an extent. And finally, the big picture that I want to be taken away, on small temporal and spatial scales, we expect extremes to exceed limits defined by entraining quasi-equilibrium in reanalysis, and human habitability may be impacted or exceeded across the tropics sooner than we expect from models. That's it. Any questions?
Anybody have?
Yes?
I'm just curious, you compared, you have a lot of hypotheses as to why. I'm curious, have you tried comparing the reanalysis to actual sounding data to see if the saturation deficits at 850 are, I'm sure they assimilate that into the reanalysis, but that's an actual point source.
I haven't. Well, that's one of the things that this plot is showing. This is from soundings, this relationship. Well, one of the problems is that there's just not that many weather stations with soundings compared to surface weather stations. So if I go back to this plot, I use 934 surface weather stations, and there's just, I have not looked at it, but yeah, I think that the difference in scales suggests that it has to be consistent, right? Like here, I actually have a plot to show. So this is what this plot looks like if you use a 1/4 degree saturation deficit versus 1 degree. And you can see there's no difference. And so there's a problem here in that It's just not consistent with this weather stations, the reanalysis, and or under this theory with this line, not dependent on scales.
So if the reanalysis would have to be far too moist,
And just in general, across everything, it just doesn't.
like everywhere at these extremes, the
Yeah.
reanalysis would have to be far too moist.
And
Yeah. So yeah, I guess you could look at whether that's the case in soundings.
yeah, that would be a good idea. Yes, Richard?
Great talk, Quinn. I have a very naive question, but based on this figure that you're showing here, have you tried, I know you mentioned about spatial distribution and spatial heterogeneity of techniques and such, but do you have figures that would show that you have a similar figure for one region and compare that with another region to see whether the exact regional biases show up or?
Not specifically. I have something similar. So first I will show you, I'll first pull up this plot. So these plots show, again, these different bins and how they react similarly. And I mentioned that there's some inherent sampling biases, and that's why we see that this bottom line is very much more stable. I have not looked at specifically how the different regions vary. That's actually more related to that previous paper. So this is only for like the northern Indian Ocean and the around there. And so what I wanted to see is the tropics on average. I will show you that, again, this binning analysis, I mentioned there's some sampling biases. This is just an example. This is how some of these extreme days are spatially located. And so on the top plot here, we have our moistest bin in the coldest zonally free tropospheric bin. And so increasing brightness is increasing density of weather station days for that bin. And see, for example, in this coldest bin, it's highly biased towards our higher latitudes, closer to 20, whereas our warmest bin is not really, it's more biased towards the center. And so there are strong sampling biases to where these bins actually lie. And for example, one other thing which I haven't shown is that the driest bins are all highly located, like around here. Yes?
Cool stuff. It's also really neat to the hypotheses for where you're going with this next. My question is, a lot of these plots, you have weather stations on one side and reanalysis on the others. Have you, like, direct head-to-head compared weather stations and reanalyses on the same plot to see, like, okay, when you have an extreme in the weather station in one term, what does that look like for the same exact location in the reanalysis? Have you done anything like that to try to figure out why they differ for each instance?
I don't.
If that's what you did, right?
Well, not for every single weather station.
I mean, like, on the same plot. So instead of, one plot the other, take,
yeah.
like, instability and then have instability weather station on the x-axis and then reanalysis on the y.
Oh, a scatter plot.
Yeah,
of
something
the-
for different terms to try to see if you can learn anything from that. Try stuff like that, yeah.
Yes, so we looked at the surface extreme. I did that for the moist static energy. Similar, so for these plots, I plotted just like instability for the weather stations versus reanalysis. And so once again, that these points, the scatter plots, are the exact same locations and times for reanalysis and weather stations. And so I did do that. And so if you plot instability for the weather stations versus the reanalysis, instability is this term, so you plot them against each other, this term just drops out. It's just the extreme surface moist static energy from the weather stations versus that location and time in reanalysis. And you see that they're not that highly related. One thing you see is that you see a similar, okay, I'll show you this plot. I'll flip between these plots real quick. You see that systematically the extremes in weather stations are higher than than reanalysis, always, for like the same days. I think always.
But the correlation was only like
But when
0.3, right?
Yeah, but when you actually look at how they vary, like outside of just, yeah, they're not that highly correlated.
Was it a correlation coefficient of 0.3?
Something like that. It was the correlation coefficient of, like you would expect them
I don't
like to be like linearly related, but they are not very strongly related.
That might be worth putting in, yeah.
Have you like looked at how these look regionally and between like oceanic and land regions to see? I'm curious to see what the approximate weights would be.
Yeah, well,
If this
what-
like generally holds across all the tropics, or if there's some variation. depending on-
Yeah, so, well, one of the things is that these weather stations are only on land. There's some like on some islands, but they're very heavily, 95% of them are on land or something like that. And so that's what I tried to get at with the binning analysis, is that by binning by saturation deficit, hopefully this will get at how things vary across the tropics rather than just the most extreme areas, which, this maximum line is only our most extreme days. Do we get variance along the saturation deficit outside of just this absolute maximum line? And so that's what these lines are somewhat showing that we do.
Other questions? Thanks for a great talk, Quinn. Yeah, and if you have any questions for him individually, we've got, I guess, 2 minutes until the room probably needs to be in someone else's hands.